All right, thank you so much for the introduction and also for all the great work that you've been doing, and also the Chinese Open Science Network. I mean, there's been a lot of work translating some of my teaching material into Chinese. So I have this online course, a MOOC on Coursera, as was just mentioned, but also a textbook that is online where you can just read through things. And several chapters there have been translated. Among others, I think the one on equivalence testing. So if you want to learn more about it, you can find it and read up on it. All right, I'll talk a little bit about change, how difficult it is to improve things, and the risks that can emerge when we try to change things, especially without really understanding what we are doing. So a little bit of an explanation of why there have been so many changes in the way that we work. And I think that people have realized over the last years that there are a number of things not going as well in science in general as we might want. And this happened a lot in psychology, which is my background. It's not limited to the field of psychology. It happens across empirical sciences. It just happens to be that psychologists have thought a lot about this. So I'll give you some examples from this domain because that's what I know best, but it's definitely not limited to this field at all. And there have been a couple of observations of things that we should improve. For example, people have recently pointed out that it's very difficult to replicate findings that other people have published, and much more difficult than we might think based on all these significant results we see in the literature. So people have said, for example, there may be a crisis in personality and social psychology associated with the difficulty often experienced by researchers in attempting to replicate published work. They're complaining here that they don't know why and how often this happens because, well, we often don't publish them. Now, Gillett has really shown that you can change this because he is doing these replications, but this is a very novel and still too rare thing. A second problem that people have identified is a theory crisis. It's nice if we can replicate things, but one of the goals of a science should be to build theories that make generalizable predictions. People have also complained about how well we have been working on this. So, for example, people say it is simply a sad fact that in soft psychology, theories rise and decline, come and go more as a function of baffled boredom than anything else. So we don't really falsify our theories, we don't really test them, we just sort of play around with things. And compared to some other fields, we don't do a very good job. All right, well, maybe you say we might not be very good at building theories, but psychology is a very useful science. So a lot of the things we can do can be applied in real life. But this is also something that people have complained about. And this is known as the practicality crisis. An example of a statement about this is, as a science directly concerned with behavioral and social processes, psychology might be expected to provide intellectual leadership in the search for new and better personal and social arrangements. I think that would be nice. There are a lot of social challenges that we could help with as a field. In fact, however, we psychologists have contributed relatively little of real importance. Not too positive. So this is also complaining that what we do in practice isn't very good. And then we have a generalizability crisis. That's the last one. I mean, maybe there are more, but these are the ones I wanted to highlight. The generalizability crisis is about the difficulty of if you have established something in one specific context, then it might not work the same across the world. And we would also need to show that it applies in other cases. And this is difficult. So here, the statement is, in the event that a result is replicable, there is little likelihood that it will be sufficiently general across minor variations in stimulus conditions to identify scientifically useful relationships. So all of these have been pointed out in recent years. You can read up on them if you want to. It seems to be a very good idea to write a paper with the word crisis somewhere in your title. It's good to get read. So maybe you can think of some other things we're not doing well and declare a crisis on this. But as you see here, the papers that have appeared on this, replication crisis, the open science collaborations work in 2015, theory crisis, papers starting to appear 2019. what I've actually been showing you in terms of these quotes are actually much older than this. So you might think that a lot of these things that we've been complaining about in recent years, that we have to do much better, are recent things that we've realized. But actually, all of the quotes that I read come from papers that are much older, sometimes half a century ago. For example, the replication crisis was already discussed in a paper by Anthony Greenwald in 1976. So it turns out that we've been complaining about this basically for 50 years, for half a century. The quote about the theory crisis comes from a paper by Paul Mill, almost as old. The practicality crisis, also more than half a century ago, people have been talking about these things. And the generalizability crisis, also something people have pointed out for decades. So it's interesting that we work in a field where people can point out the same problems for decades without us really doing a very good job in solving them. But maybe you think, okay, Daniel, don't be so pessimistic. Surely we've seen that a lot of nice things are going on. And Gillet's talk shows that we can, of course, improve things over time. So maybe you'd say, we are doing things a little bit better, but it is just very difficult to do the right thing. And it was interesting to hear Gillet say so much like, well, if your university requires that you publish in a journal with a good impact factor, then be aware that this journal doesn't have an impact factor yet, but it will get a good impact factor. Yeah, so there's a lot of pressure to publish certain things. So maybe you'd say, yeah, this is what makes it so very difficult. And now especially, here's a quote about this publish or perish culture. So it's somebody who wrote, if it be true that for the time being, at least, the quality, this is about sociology, again, it's cross fields, the quality of American sociological writing is in inverse ratio to its quantity, the reason is to be sought, among other things, in the fact, first, that the system of promotion used in our universities amounts to the warning, publish or perish. And this is something that I think many people experience. And you might think, okay, yeah, this is really the problem. It's becoming more and more difficult to just do good science because of this publish and perish culture that has emerged. Well, if you think that that is the reason that things are especially difficult now, I again am sorry to have to tell you that this quote is also basically a century old by now, comes from a paper by Case in 1927. All right. So we've been complaining about these things for a long time. I'll give you one more, and then we'll move on to some things that we can maybe do about this or what the causes of these problems are. This is a quote, social psychologists must find ways of adjusting to or moderating academic pressures to publish at the same time that they reduce their own rate of publishing findings that are so incomplete as to be misleading. So this is a call to publish less, but do better research. And this comes from Elms, 1975. All right. So it's clear that a lot of the problems that we're trying to address are problems that have been around for maybe a century, or at least half a century. They're very old and difficult things that we're trying to solve. I think it makes sense to wonder, so what is really the problem here? Why has it proven so difficult to do something about these issues if we have been pointing them out for such a very long time? And I guess if you're maybe a little bit younger and you're like, well, this is all the fault of older people doing things wrong. But surely we've seen that things are slowly moving along in the right direction. And I'm definitely optimistic about some of the developments that we've been seeing in the publication landscape. Things like registered reports are indeed very nice. Pre-registration, good practice. So they lead us to solve certain things. But I think that there might be some underlying core of the problems that have been pointed out for a long time that really are difficult to address. And I want to point this out, especially with a focus on statistics. I'll give some examples in the domain of statistics, mainly because this is the field I work in most. And this is the fact that even if we try to improve things, there is a risk that we do so still relatively mindlessly, that we maybe change our ways a little bit, but we still don't understand why we're doing things in the right way, right? All right. So we can hope, of course, that we're thinking of how to do better science now, and that will lead to improvements. But I think we should be worried that some of these improvements are just the same kind of mindless heuristics in a different way. So one thing that people have been pointing out for the last decade, or maybe by now, more or less 15 years, is the fact that we have been analyzing our data with too much flexibility. And when I talk about flexibility, I mean that you can analyze your data like this. You can add a different variable. You can remove some participants if they had extreme values or decide not to, just based on whether the analysis look better and give you the result that you want. And many people admit that these are practices that they have done in the past. And one of the reasons that we have created these registered reports is so that we give people the option to just publish the data as it is without having to search for significance. So you might say, well, it's nice. Now we work in an age where people have stopped flexibly analyzing studies and they stick to this 5% error rate. Okay. Now, one thing that I like to do sometimes is ask scientists, okay, so we're doing this practice, but why are we doing this practice? Because I think that's a question that you should be able to answer at least once about something. Now, of course, I mean, there are layers and layers and layers and reasons behind reasons behind reasons. So you can really dig deep into any specific topic. But here I'm really saying it would be nice if you can just tell me, if I say, so why do we actually do this? You can give me some sort of answer. So if we are so obsessed now with controlling our alpha level at this specified 5% error rate, well, then maybe a good question is, why do we use this alpha of 5% to begin with? Because we all do, right? If I would read your papers, if I would open them, there's probably somewhere that you use this alpha level. And if your p-value is smaller than this alpha level, then you're allowed to make a claim and otherwise not. So why do we actually do this? Well, one thing that I like to joke is that this is something that was written down as one of the 10 commandments when Moses went up to Mount Sinai and received the sentences from God about how we should live our lives. I'm not the first to make this joke. There's a philosopher of science called Ravets, who published in 1971, those who have any craft skill in the use of such tools, and he means hypothesis testing, will appreciate that the significance level to be adopted is not assigned by God, but must be decided by the user. So there's nobody who tells us that it has to be 5%. We have to think about this. And I think he makes a very interesting observation in this same paper by quoting, again, a comment from Berkeley, which is centuries old, but I think still relevant today, and basically the core of what I want to talk about here. And he says, look, the real underlying problem we have in science is that people really don't think so deeply about why they do things. They just copy things, they imitate, they do them because other people do them. And this is nothing new. It is apparently a central thing that has been going on, in this case, for centuries. So what Berkeley writes is men learn, he says men, but he means people, of course. People learn the elements of science from others, and every learner has a deference, more or less, to authority. So that means we respect authority. He writes, especially the young learners, few of that kind, caring to dwell long upon principles. So when you're young and you're just starting, you don't really want to think about all these things and learn about them. You just tell me what to do. Tell me what to do. Okay. But inclining rather to take them upon trust. So if somebody tells you what to do, you just believe that that's the right thing to do. You don't wonder why we do things in a certain way. You just accept it. And then he writes, and things early admitted by repetition become familiar, and this familiarity at length passeth for evidence. So this practice where we just do things, we look at what other people are doing, we trust that there's a good reason why we do it in this way, and then that just becomes habitual, we get used to it, and we accept it. And that process is, I think, often really at the core of what we are doing. Not just with statistics, although maybe statistics is a very good way to see how this plays out in practice. But this practice of just accepting things without carefully thinking about them, respecting authority, thinking, well, if that's how we do it, that must be how we do it. It's probably one of the most important lessons as a young researcher that you can learn, that often people do things without really knowing why they do them. All right. So in the case of the alpha, where we set the alpha, if we go back and we actually read the original papers by people who discussed this topic. So for example, this is Fisher. This is early in 1925, I think, this book. Then Fisher writes that it's just a convenient convention that we put it at 5%, and we can put it anywhere else where we want to do it. So here in the top, he says it's a usual and convenient for experimenters to take 5% as a standard level of significance. But there's no real reason to put it there. You can put it anywhere else. The people who really promoted our current way of doing hypothesis tests in the sense of setting an alpha level, computing statistical power. So the hypothesis testing procedure that you see more and more formalized in scientific journals over the last years, because we realize we're not doing it so formally. Well, this approach is mainly by Neyman and Pearson. So we're trying to control our type 1 and type 2 error rates when we make scientific claims. And this is a paper where they discuss how we have to control these error rates. And they do something that's very interesting, because often statisticians kind of like to tell us what to do, but they don't. They actually say, well, how you set these error rates is very difficult. It depends on the costs and the benefits of what you're studying and how bad a type 1 error is and how bad a type 2 error is. They have a nice metaphor about convicting people. What if you incorrectly convict somebody when they're free? Or what is the cost of letting somebody walk free when they're actually guilty? And then they make a very smart comment here, rare for people in statistics, I think. They say, we can't tell you what to do. From the view of mathematical theory, all we can do is to show how the risk of the errors may be controlled and minimized. The use of these statistical tools in any given case, in determining just how the balance should be struck, must be left to the investigator. So it's up to you to determine where you put these kind of error rates. And we don't. We take them sort of mindlessly from the literature. I have this example that I often use, which is my favorite example of making a real cost-benefit analysis. So this is a koala. It's based on a study from ecology, where they take a look at whether they should test if the koala population is declining over time. So they can, of course, test this. They can count and do a test. Is there a reduction in the amount of koalas? And if so, if there is a reduction, they can choose to intervene. But in this paper, they actually say, but what is the real cost and the benefit of intervening? There's a cost of the intervention, and there's, of course, also a cost of the population going down. And what if we miss it? What if the koala population is declining, but we miss it in our tests, so we make an error, right? So how costly are those errors? And then it comes down at the fact that it's just cheaper to always intervene. In other words, they basically say the alpha level here should be set to 1. Now, that feels very weird if we're scientists. It might be like, wait, what does that mean? It means we don't have to test. We will treat the situation as if there is a significant decline. We're basically always intervening. Now, we can talk more about how we sometimes actually also do this as scientists, because we don't always test things. Sometimes we just make a decision without any data. And if we make a decision, for example, should we do our experiment like this or like this? Well, if you want to have an evidence-based decision where you control error rates, you could do a pilot test and you could figure it out. But often we don't do this at all. We just make a gut feeling decision, like, well, let's do the experiment like this. I think it's better. Well, in that case, we actually accept an alpha level of 1. Anyway, maybe too much detail, but the main point here is that if you carefully think about where this alpha level should be on a case-by-case basis, it shouldn't always be at 5%. All right. Now, I talked about the 5% alpha level, which we mindlessly have adopted. And I think it's fine, of course. I mean, sure, that happens. Then an interesting question is what we also said, we were controlling our type 1 error rate and our type 2 error rate. So when we talk about the type 2 error rate, people often recommend to go for 80% power. Maybe you do this in your own research. If you design a study and you go through, as Gillard recommended, this nice registered report format, you go and you submit something to peer community in, well, then they want you to design an informative study. That means an informative study means we'll learn something from it. So it means that you make sure that your type 2 error rate, or 1 minus the statistical power of your test, is high enough. So the minimum recommendation here is often 80%. And of course, people just follow this. You can set it at 90%. You can set it at 95%. But most people, I think, if I again would find your power analysis, if you've performed them, will say something like, well, and for an 80% level of statistical power, we need to collect this amount of data. All right, so let me do exactly the same thing I've done before and just ask you a simple question. Why? Why do we aim for 80% power? Why not 90 or 95%, for example, as a default? Well, here again, what we can do is we can read what actually was the argument behind a power level of 80%. And if we do this, then we come across the work of Jacob Cohen, who wrote a book, Statistical Power Analysis for the Behavioral Sciences. This book was quite impactful, not just in the behavioral sciences, but actually beyond. It's one of the rare cases where this recommendation for 80% power isn't just present in psychology, but we have actually influenced people in the field of, for example, medicine. They also didn't really know which power to go for, and they just sort of copied this 80% often. It's interesting because most of the time we actually learn from them. So it goes the other way around. For example, a practice of equivalence testing, as was mentioned, has been developed half a century ago in pharmaceutical research, and now we slowly start to adopt it. But this was one of the cases where we came up with something and it spread to other fields. So then, okay, let's hope that we did a good job in making this recommendation. So let's read what the argument is that Cohen based on when he recommended us to go for 80% power. Okay, so here we read the explanation, right? It's from his book. It is proposed here as a convention. There we have that word again. A convention. It's just a thing we do without really thinking about. It's proposed here that as a convention that when the investigator has no other basis for setting the desired power level, so if you can't think of anything else to do, then you use 80%. Okay, and why, Cohen? What's the reason? This means that the beta, the type 2 error rate, is set at 20%. This arbitrary, he says it's just arbitrary, but reasonable value is offered for several reasons. Cohen, 1965. Well, you can take a look in Cohen, 1965. There's not a lot extra. So the main thing, and he says that here, the chief among them takes into consideration the implicit convention of an alpha level of 5%. So we're building conventions or heuristics on top of other heuristics now. Now, that cannot be a very a very stable basis for a science. If we start to build conventions on top of other conventions, we do this heuristically because we do this other thing heuristically, feels like it's not going to be a very smart thing to do, but okay. And then he says the beta of 20, so 20% type 2 error rate, is chosen with the idea that the general relative seriousness of these two kinds of errors is in the order of 20% in a ratio to 5%, or in other words, the type 1 errors are of the order of 4 times as serious as type 2 errors. Cohen thought that a type 2 error is 4 times less serious than a type 1 error. Why did he think this? I don't know. It was just his gut feeling. That's it. So we have an 80% level of power as a minimum in our field because of the gut feeling of one person who wrote a book, who based this gut feeling on the implicit convention of using a 5% alpha level all the time. Does that look like an impressive basis to build a practice on? I'm not so sure. I think this is a nice example of what Berkeley mentions. We take things upon trust, we become familiar with them, and through repetition, we think that this is just how we're supposed to do it. So why do scientists set these error rates, type 1 error rate, type 2 error rate, at rates where I don't think most of the time this is actually what they really care about? This is not the real error rates that they want. Well, the main reason for this is that we just follow norms. And maybe this is also a little bit of the reason or a little bit of an answer to the question, why don't things change more quickly, for example? Why is it so difficult to move to better research practices? Well, because most of us are just used to following norms. We don't question why we do certain things. We're too busy doing our studies, publishing our articles, making our university happy to really sit down for a moment and think, wait, why is it that we're doing this? I mean, I'm sure that somewhere in your career, when you were very young, you had a question like this. You were thinking, why do we do this? Why do we do this? And maybe you were too scared to say it out loud because you thought that it would make you sound stupid. If you ask the question, I'm sorry, I've been doing it for the last 3 years, but why do we actually aim for 80% power? Why not for 90 or not? I think that some people, if they wanted to say this out loud, they would be worried that it's a stupid question. It's not a stupid question. But I think some people might not even want to ask it. Or if you were brave enough to once ask this when you were younger, you're like, why is it actually that we do this? The answer you get was probably very unsatisfactory, something in the sense of, well, we do it because this is what we do. And that's it. All right, so I want to give you a couple of more examples in statistics beyond this type 1, type 2 error, where I think we do things rather mindlessly, just to make this point that we can change the way that we do things. Sure, we can tell other people, now you should do it like this. But that there is a real risk that if we try to make these improvements without building any actual understanding of what we're doing, that these new improvements are just new heuristics, we're not actually going to improve anything about how we do science. So we talked about the tendency now to be very strict in our type 1 error rate. So we have a 5% error rate, and we want to prevent flexibility. We don't want people to mess around and test like this or like this. Well, one way that we used to do this, and I remember this from being a student, when I was a student, this was actually how we were taught to analyze data. So we would be in the lab maybe for 5 days. We would have reserved the lab space for 5 days. But we would also get our data at the end of the day and already put it in our data analysis software, run the analysis, and then maybe after 3 days, if the effect we were looking for was already statistically significant, well, we could tell our colleagues, hey, I don't need the lab anymore. You can start to use the lab space from tomorrow. And people would be very grateful because there's only so much lab space. There are a lot of people who want to use it. So we thought this is very efficient. And of course, then we did not realize that if you test, you collect data, you test, you see if it's significant or not, you stop if it's significant, but if not, you continue on. Next day, you test. If it's not significant, you go on, that we are doing multiple testing and we are inflating our type 1 error rate. I mean, nobody taught us this back then. Now, we have taught people that this is a problematic practice. It is what some people call a questionable research practice. I don't really like this label, questionable research practice. It's just a bad research practice. You inflate your type 1 error. You reduce what we call the severity of a test. If you do certain practices, you reduce the probability that you will prove yourself wrong. And that is one thing that I think is really important when we do tests in science. We should make it difficult to be proven right. Only when we're actually right about our hypothesis should we find a significant result. A lot of these practices where we flexibly analyze our data increase the probability that we'll find what we want to find, but we will be wrong about it. So that's called severity, test severity. It's an important thing of why we do things like pre-registration. I'll come back to it in a bit. One of the ways that we reduce the severity of a test is by collecting data, testing, collecting data, testing. So we told people, you're not supposed to do this. And many people, if I now educate them about statistics, will say, oh no, this is really bad practice. You're not supposed to do this. You cannot look at your data and then decide whether you go on or not. But this is not true. Of course, you can do exactly what we did when we analyzed the data after the first day and after the second day and after the third day, with one important difference. You control the alpha level across looks. If you have 5 days in the lab and you want to analyze your data 5 times, well, you have a multiple testing problem. You can do this in advanced ways, controlling the alpha level. It's called sequential analysis. The easiest way to correct it, if you don't want to learn about this at all, is to do a Bonferroni correction. And you've probably heard about the Bonferroni correction once. So this is where you take the alpha level and you take the number of tests. If you have a 5% alpha level and you have 5 tests, then you do every individual test at 1% alpha level. That works. So it's a very easy way to allow you to have this flexibility. If you're done and somebody else can use the lab, so it is efficient. So this practice of sequential analysis exists. It's very old. It's done a lot. But if I tell people about it, they think, no, but that is p-hacking, right? That is doing this questionable research practice. Instead, it is actually a very useful thing to do, and it's done in many large studies that are run by professional statisticians, because it's a good way to save time and money, and it allows you some flexibility along the way. So why don't we use those kind of techniques more, right? Well, probably because we've scared people into thinking that this is p-hacking. All right, so maybe the experimental design, we didn't really get there completely. We've taught people about problematic research practices, but they don't really understand why they were problematic. And now they're over-responding and thinking that things that are fine are bad. Okay, so maybe we have some work to do there. Let's take another thing that we have improved. For example, how we report and interpret statistics. Now, in the 90s, people would rarely, if ever, report effect sizes. And Gillett showed this very nice book, this open access book, where you can look at how you can compute effect sizes. I've seen it. It's a lovely piece of work. Highly recommend going there if you want to report effect sizes. But what we see is that there is actually, in practice, still this kind of mindless thinking about effect sizes. And I'll give you one example. And this has to do with the use of benchmarks. So it's difficult to interpret an effect size. It's quite easy to report them. We can compute them. But what do they actually mean? So what we see is that people use benchmarks that Cohen proposed for what a small, a medium, and a large effect is. Now, maybe you know them by heart. Otherwise, you could look them up. They are mentioned in this open access resource, for example. I'll give them to you. The benchmarks that people use for Cohen's D and R in small, medium, large is a Cohen's D of 0.2 or 0.5 or 0.8, or in a correlation, the correlation of 0.1, 0.3, and 0.5. And you can go to Wikipedia. This will be on Wikipedia. It will say the same. I mean, these are the benchmarks that you're supposed to use. Now, it's also possible to compute the correlation from the cohens D. These are two effect sizes, but you can convert one into the other. Again, the book that Gillett mentions has a website chapter on how to convert effect sizes. You can get these formula there. But let's do it, okay? Let's just convert a cohens D of 0.2. We plug it in the formula in the bottom on the left. We enter our cohens D, and then we compute the correlation, and the correlation is 0.1. So those match, right? This is cohens D small benchmark. Of course they match. We can also do it for a medium effect, but then they actually don't match. Remember that a correlation of 0.3 was considered medium. Okay, it's a little bit off, maybe not too far, but still. We can also do it for large. We convert one into the other. Here it becomes a little bit bigger. So we had a correlation of 0.5 on the previous slide. We consider this a large effect, but if we actually convert the cohens D into a correlation, they don't match up. It's kind of weird, right? So we have this practice of using benchmarks and say this is a large effect. We have learned what the benchmarks are for a correlation in a cohens D, but they don't even match up. They're not coherent. The reason that they are not coherent has something to do with the way that they are computed in Cohen itself. So here you see the benchmarks that I just mentioned. So here's the computation of them. Where does this come from? Well, actually, Cohen computed benchmarks for a different kind of correlation than we use most of the time. So this is something that has to do with the fact that if you carefully read what Cohen suggested, it works perfectly for the correlation that he proposed the benchmarks for, but we use them for a different type of correlation that we use more often. People have pointed this out for a long time. McGrath and Meyer in 2006, for example, say these benchmarks don't even line up. There are a lot of people who say you should not use benchmarks, but people still do. And I think this is a perfect example of something that we do rather mindlessly. We don't really know what we're doing. We've seen other people tell us, yeah, correlation of 0.5 is large. Correlation of cohens D of 0.8 is large. But then if we compute them into each other, they don't match up. We could also convert them the other way around. We can take the correlations of 0.1, 0.3, and 0.5 in the bottom of this figure, and then we say, okay, a cohens D of 1.15 is considered large. We can do it either way. I think the real thing to do here is not use any mindless benchmarks at all. It just points out something that I think really illustrates this idea of we didn't think carefully about it. We've heard people tell us again and again. We've taken this over. It's become so familiar. We don't question it at all. It's a norm. It's a mindless heuristic. There's some other things like this that I really find interesting. One is that very often people in their introduction will write, we predict that the score in group A is larger than the score in group B. But then if they do the test, they don't do a directional or a one-sided test. They do a two-sided test. Why do we do a two-sided test most of the time? Well, this has something to do with the fact that people didn't really trust other researchers in the past, that they actually wanted to do a one-sided test all along. This is nicely discussed in this text by Bacon in 1966. Bacon, I think it is. So it should be spelled differently, his name, Bacon. He writes, it is manifestly contingent, the choice for a one-sided or a two-sided test, on the decision of the investigator to, or whether to run a one-tilt or a two-tilt test. So how to do a hypothesis test is contingent on whether you decide to do a one-tilt or two-tilt test. And then he writes, and somehow making the decision after the data were collected and the means computed seemed like cheating. Well, it is cheating. I mean, it is just one of those sources of flexibility. If you decide to use a one-tilt test only because it will make your effect significant, yeah, then you are just p-hacking. You're inflating your alpha from 5% to 10%. So you're doubling your type 1 error rate. That's not a good thing to do. All right, so we shouldn't do this. How should this be handled? And then Bacon writes, should there be some central registry in which one registers one decision to run a one-tilt or two-tilt test before collecting the data. 1966, people. More than half a century ago, he is basically proposing registered reports or pre-registration. We didn't have computers back then, of course. We can't log into some sort of website and create a registration. So he has a nice example of how you could do it in this time. He writes, should one, as one eminent psychologist once suggested to me, send oneself a letter so that the postmark would prove that one had pre-decided to run a one-tilt test, because the stamp on the letter will show what the postage date is when you had this idea. Okay. So this is another kind of thing we do relatively mindlessly. Why? Because in the past, people wouldn't trust us. Now we can register whether we want to do a one-tilt test or not. And then we can become more efficient when we test things. If we're not interested in effects the other direction, we don't have to spend type 1 error rate in the other direction. So we do more efficient tests. We have higher statistical power with the same sample size if we do a one-tilt test. Why don't we do it? Good question. If we ask editors of journals, what is your opinion about a one-tilt or a directional test? Do you like it or not? It greatly depends on whether people have pre-registered or not. So here we have a scale, an attitude scale. I asked editors, what do you think of directional tests? 1 is I'm very negative about it. 7 is perfect, do it. And then we see in the top the attitude if people get a one-tilt test and it is not pre-registered. Editors don't trust you at all. They don't think that you wanted to do a directional test. They're quite negative about it. Scores mostly on the left. Some people are trusting. Some people are still positive about it, but largely not. The opinion of editors when it is a pre-registered one-tilt test is much more positive. Some people still don't like them for some reason, but most people say, yeah, this is perfectly fine. So we can solve this problem, right? We can solve this problem by pre-registering and then doing a one-tilt test. Even though I'm telling you it's more efficient, it's coherent, this is the correct test to do, given if that you had a prediction, right? If you had a prediction, X is larger than Y, that's a directional prediction. I think many of you will still not do a directional test. You will not pre-register and do a directional test just because it's against most of the norms. Mostly people do two-sided tests, so norms are strong. Maybe you'll prove me wrong and you'll go and do a directional test, but I don't think you will. I think you will keep following norms. Maybe prove me wrong. All right. Well, maybe the statistics reporting is not so well done, but surely things are better in other directions. We're sharing data, we're sharing code, we're pre-registering, for example. Isn't that nice? Well, yeah, it is nice. But then if we take a look at how we do these things, it's often just not done very well. We have a paper. It's already a couple of years old, so I hope things will have improved over the years. But in this study, we took a look at registered reports, early, some of the first registered reports that were published. So these are people who really want to do the right thing, right? They're motivated. These are the early adopters of this format. We ask them, so if you pre-register or if you did a registered report, is there data sharing? Is there code sharing? And can we then actually reproduce your results? And from the studies, the final data set here includes 62 registered reports at this time. And then if we go through and we try to reproduce them, we can do this for about 21 of them. So about a third. Report data and code in a way that's good enough to then reproduce the results. Now, we should not be surprised by this. It's difficult to do things well. We see exactly the same pattern in other meta-scientific studies that take a look at how well are people pre-registering. Yeah, people don't do it well the first 1 or 2 times. If you really are motivated to learn how to do these things well, then you dig in, you learn the basic principles, and you do it in a way that we can reproduce things. We can do it for 21 here, so some people are doing the right thing. But if you are going to share data and code just because that is now the new norm, well, then I think we can expect this pattern to continue on because people just think that they will do it because they have to do it. It's the new norm. Many people sometimes even say this of pre-registration. Yeah, you have to pre-register now. It's what they expect. And then they do it. They don't understand the basic principles. They don't really care about it. They just do it because other people do it. And then quality is often low, and we don't really have much benefit of these registered reports, or these, sorry, not registered reports, the pre-registrations. A big benefit of registered reports is that they are peer reviewed. So the pre-registration is peer reviewed. So if you didn't do a good job, you'll hear it from the reviewers. But I'm talking about studies where people pre-register on their own and nobody looks at the pre-registration. Maybe ever, but maybe only after all the work is done and it's submitted for publication. There we often see the quality is just not very high. All right. So I think you'll get the basic point that a lot of the changes we're implementing to improve things are still mainly based on norms and not really on sort of principled justifications, where if I ask you, why do we do this? You can give me a confident answer. And with a confident answer, what I mean is that you put your hand on your stomach and you say, this is why. This is the answer. And you don't feel like you're cheating. You don't feel like you're bullshitting. You know what you're talking about. That feeling, the feeling of confidently saying, I know what I'm doing. I'm not just doing it because other people are doing it. I know what I'm doing. That feeling is pretty rare, but that is what we should have as scientists. All right. Now, this practice of following norms sometimes takes quite explicit forms. This is a paper that I personally found quite annoying for exactly this reason. And it is about how to do tests. And the authors of this paper say, well, people are abusing flexibility in data analysis. They're messing around a bit too much. We use this 5% alpha level. Well, how about we lower the 5% alpha level? We think people should use an alpha level of 0.005 instead of 0.05. We have to become stricter because things don't replicate, and this is a good solution. All right, you can think that that's a thing to do. You can do something like a cost-benefit analysis and say, look, this is how costly a type 1 error is, blah, blah, blah. We lower the alpha level, as in the paper by this field with a koala. You can do something like this. That's not really what they do in the paper. They just say, why should you do this? Well, statisticians have known the relative weakness of a p-value 0.05 for a long time, for a threshold of discovery. We are not proposing anything new. People had proposed this before, it's true. Okay, so what changed? A critical mass of researchers now endorse this change. Why should you do it? Because of a principled underlying argument? No, that's not their point. You should do it because other people are saying you should do it. You should do it because this is now the new norm. These important people on this paper think you should do it. That goes against, very strongly against, what I think science should be. All right. Nevertheless, we have these people in all sorts of ways confidently saying this is now how you should do things. And they're often wrong. I'll give you some examples of things that people have emailed me about, because this happens, right? About statistics. People sometimes say, Daniel, we got this from an editor or from a reviewer. They're telling us this is now how we should do it. But does this make sense? So I'll share some examples. For example, an editor at a prestigious journal replied to authors saying, your sample size is too small. You need at least 250 participants now. All right. This is a new norm that some people are promoting. Where does it come from? Well, let's do what we did before. Let's read the original articles and see what the real underlying arguments are. This recommendation comes from a very nice paper in many ways by Schoenbrod and Perugini. They say in the paper, probably because a reviewer said, can you just summarize the main points, please? If table 1 should be boiled down to simple answers, for typical research scenarios, reasonable trade-offs between accuracy and confidence start to be achieved when n approaches 250. So an editor read this and said, well, you need 250. But if we take a look at the table itself, well, depending on your actual scenario where you're in, the sample size you need might be as low as 20, or it might be as high as 270. So let's not summarize table 1 in one easy-to-use heuristic. Let's understand the principles that were used to generate these numbers and have a real case-by-case solution based on the principles, not on some heuristic. All right. I already mentioned sequential analysis. People have said you can't really use this anymore. What you're doing is p-hacking. It is not. Sequential analysis, of course, exists. And for example, the COVID vaccine was tested in a sequential analysis because people just do this in these large trials. Another example, you need to do a power analysis for the sample size justification. Somebody complained that a reviewer of a grant had told them this. No, that's not true. A power analysis is only one way to justify a sample size. There are many other approaches that are equally valid. So again, don't overuse one type of heuristic. There's some people who say all studies should be pre-registered, or even all studies should be registered reports. Now, I mean, I love those formats. They do something very well, but I don't think all studies should be pre-registered. It depends on what you're trying to achieve. I have specific opinions about this. Maybe we can go about them in the questions, but I mean, I don't think we should use sort of blanket rules, universal rules. Why do we pre-register? Well, there's a very specific reason. It has something to do with the fact that we want to allow other people to see that we severely tested a prediction. So if you don't make any predictions and if you don't do any tests, well, I don't really know what the argument for pre-registration is. Right? All right. Another example, we should all do Bayesian statistics because that's much better and people do p-values wrong. Yeah, many people do p-values wrong, but meta-scientific studies also show that many people do Bayesian statistics wrong. So, I mean, switching isn't really a good solution. All right, so I think one of the main points here is that what we're trying to do is improve scientific practices, which is really important. But what we need to realize is that these improvements will not lead to anything if all we do is teach people new mindless norms that they can follow, that they can imitate without understanding anything. I've been trying to promote this hashtag online, justify everything. That's maybe a bit difficult. Maybe it's very difficult to justify every choice. Maybe it's asking a bit too much. I have an alternative, less sexy sounding hashtag, which is at least ask why? Why do we do this at once about everything that you do in your life? All right. So there are many reasons why not understanding basic principles could lead to justification. For example, about pre-registration. Why do we pre-register? Is it just because it's the new thing to do? Some people have arguments such as, well, it helps you to think about your hypothesis. Sure, it does help people to think clearly about their study, but so does sitting on your hands and not doing the research before you have actually thought about it. You don't have to make a public time-stamped document to just think. You can just sit in your chair and think. So that is not the core reason to pre-register, right? So we have to have good underlying arguments for why we do a new practice. All right, so all these open science practices should achieve a well-specified goal. They're never a goal in themselves. And there's a very big risk that if we use them as heuristics, so we don't think about what we're doing, they become goals in themselves. And that's not what we want to do. So we always have to think, what are the goals that we're trying to achieve? How can we achieve them with this new solution? And do we think that they will be successful or not? So for example, for pre-registration, as I already explained earlier, I think my argument for this is the goal is to allow other people to see exactly what we've done so that they can see how severely we tested our prediction. And I would even say that that means that, you know, if you pre-register, the analysis is not automatically better than if you didn't pre-register. It just makes it possible for other people to see what you've done and evaluate this. And this is desirable. But for example, it would be illogical to say all pre-registered tests are better tests than non-pre-registered tests. That doesn't follow from basic principles. All right, now I know that justifying all these choices is really tough. It's difficult to do. It takes time to learn about these things. You have to read and think And that takes a lot of time. And if you have to do it about every little decision in your paper, then it's not even possible. You don't have the time to reflect on every little thing. So what would be a solution? A solution is that you don't have to think about every little thing yourself. We can collaborate. We can work together. There's only so much you can know by yourself. And this is one of the reasons why you have to resort to so many heuristics. You don't have the time to learn about everything you do. Science is too complex for this. Well, if that's the case, then we should collaborate. We shouldn't do science in small groups of people, 3 or 4, because they can't know everything. We should have much larger collaborations, work with people that have specific specializations, that know about things that can help us, right? We need the support of experts. All right, so if we want to raise the bar in these kind of improvements in science that we're doing, we really need to realize that we cannot just teach all these new practices as new heuristics, as simple things to do. We need to realize that we have to think carefully about what research is worth, figuring out the justifications for why we make certain things and do certain things in a certain way. That will take a lot of time. It will be more difficult to do good science. So we need to think, for which studies is it worth doing good research? That's also a very difficult question that I think is better in a personal conversation, which research is worth doing well. But this is the core of the issue. We can't do heuristics. We have to think about principled justifications for things. This takes more time. That's why it's so difficult to improve the way we do science. And it requires us to think carefully about, so if we want to do a good job, and it is going to take more time, which kind of studies should we be doing in more large collaborative research projects? All right. Thanks so much.